The first operation we can do on sets is the intersection between two sets, which mathematically we can write as the intersection of A and B. The second operation is the union between two sets, which mathematically we write as a union between A and B. So it's really the same symbols, just upside down. So one way to remember it is union has the same symbol as the letter U. And then the other symbol will obviously be the other option, intersection. So we can represent these operations using Venn diagrams. So I'm going to have one circle in space for set A, and I'm going to have another one for set B. We'll have the same thing for each of our operations. So for intersection, there's two ways you can remember this. You can either use the word intersection, so you're only going to highlight the area where A and B are intersecting, so this area right here. Or you can use the fact that this symbol looks like the and symbol we learned in propositional logic. So you should only highlight the area that contains the elements of A and B. So the area that contains the elements of A and B is this area right here. It's literally the intersection between A and B. That's why it's called intersection. Now let's use our Venn diagram to come up with the formal definition of the intersection, which you will use in your proofs. So you have to know this. So the intersection is equal to, at the end of the day, it's going to be a set of elements, all of the elements in here, which we can represent as X. So all X, all elements in the universe. So ideally we have a box, and it's the universe of all elements, of all X values here. But what we want to do is filter out those X's. So out of all of these X's in the universe, we only want those in here. So how can we represent that? Well, that means that those X's would have to be both in A and in B. In A and in B. So we only want the X's in the universe, the elements in the universe, such that those X's are in A and those X's are also in B. One way to remember it is, again, think of this as the and symbol. So just remember that the elements have to be in both of them. Now from now on with the rest of the definitions, I'm going to remove this part because it is assumed that you know that all of the elements that we're talking about are from the universe. So from this invisible box that we have here, but we don't draw. Now for the Venn diagram for union, just look at the symbol. It reminds you of the or symbol from propositional logic. So you're just going to highlight the area that includes the elements from A or B. So that's this area that includes elements from A, so that's good. This area that includes elements from B, so that's good. And even this area that includes elements from both A and B, but it satisfies the condition that it includes elements from at least one of them. So basically we're shading all of the area here. So now let's use the Venn diagram to come up with our formal definition. So the union of set A and B is going to be equal to the set of all elements, so of all X in the universe, again, I'm not going to write that, such that, well, the X can be in A or in B. Or you can use this symbol, think of it as an or. So such that X is an element in A or X is an element in B. So it's the same definition, just change the symbol. The third operation is the difference between two sets, which mathematically we can represent as A minus B. With a Venn diagram, let me just go ahead and copy and paste it over here. You read this as everything that's in A but not in B. In other words, you don't include anything that's in B. So you only include everything that's in A but not in B. So this is the area here that we're shading. Now, how do we represent that mathematically? Well, the set of all elements, all X, that are going to be in the difference between A and B are all X in the universe. So again, there's a box here. There's so many X's. There's X's all over the place, but we only want the X's here. So how do we define that? Well, we want all X in the universe, but again, I'm not going to write that, such that, well, what can I say about these X's? Well, they're in A, but they're not in B. So you just say that. The X's are in A, and they are not in B. And here, the not B will help you remember that X cannot be in B. And finally, the last operation we have is the complement of a set, which is just a fancy way of saying the opposite. We denote it as A bar or A complement. So C for complement. Since in this case, we're only dealing with one set, we're just going to have to represent one set. So the idea with the complement is if you have A, then the opposite of A is going to be everything outside of A. So this is where it's useful to consider the universe of all elements. So this is the universe of all elements. If you have all of these elements and this is A, then A bar or A complement is going to contain all of the elements outside of A, so all of these elements here. So in other words, we shade everything outside of A. So in this case, A complement is equal to the set of all X, all elements in the universe. So all of the X's in the universe, all of the elements inside this box, such that only the ones that are outside of this circle, so only these ones. In other words, such that these elements, these X's, are not in A. So such that X is not in A. But again, you can write it without this. So all elements that are not in A, that's how you define the opposite of A. So think bar, opposite, not A. So those are your formal definitions. You need to know these for your proofs. So anytime you forget, you can always go from the Venn diagram to the definitions, or use the fact that these symbols look really close to each other. But to put this into context, let's do some examples. So we're given these three sets. This is the universal set, so these are all of the elements ever being considered. So to get the picture, we have a box called U. We have all of these numbers in that box. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And out of all of those numbers, set A contains the numbers 1, 2, 3, and 4. So this could be set A, and set B contains the numbers 1, 5, 8, and 3. So this could be set B, and so that's the picture. So you can use the picture to find the intersection, union, difference, and complement, but I'm just going to show you how to do it by just looking at the sets. So the intersection of A and B, just look at the symbol, it reminds you of the and symbol, so you're just going to include all of the elements that are in A and B. So 1 is in both A and B, and 3 is also in A and B. So it's just 1 and 3. To find the union of A and B, just look at the symbol, it reminds you of the or symbols, so you're just going to include all of the elements that are in A or in B. In other words, all of them. Just remember the picture, it's all of the values are shaded here. So it's just going to be 1, 2, 3, 4, and then 1, 5, 8, 3. So 1, 5, 8, 3. So when you think union, think everybody being united together, everybody joined together in the same place. So think all, everybody. So you're just going to put every single element from both sets. But also think unique. So U for unique as well, because sometimes they'll have repeating elements like 4 again, and you can't put 4 twice because remember, sets don't have duplicates. So keep that in mind. And then the difference, A minus B, just read it like this. It's all of the elements in A minus the ones in B. So the set is going to include all of the elements in A unless they're in B. So 1 is in B, so you're not going to include 1. 3 is in B, so you're not going to include 3. So the only elements that are in A that are not in B are 2 and 4. So it's just going to contain the elements 2 and 4. And then the complement, the opposite of A, is just going to be everything in the universe that's not in A. So again, the picture is if A is 1, 2, 3, 4, so 1, 2, 3, 4, then everything else is 5, 6, 7, 8, 9, 10. So if this is A, not A is everything else. So we just don't include any of these numbers and we're left with 5, 6, 7, 8, 9, 10. So these numbers right here. So A bar is equal to the elements 5, 6, 7, 8, 9, and 10. So these numbers go away. And that's it for this video. I'll see you in the next.